Alright, so let's take a look at this work in class for 4.9 up a little, down a little. So, one of the most common applications of exponential growth is compound interest. For example, Mama Big Bucks puts 20,000 in a bank savings account that pays 3% interest compounded annually. So that's every year. Compounded annually means that at the end of the first year, the bank pays Mama 3% of 20,000. So they add 600 to the account, because 3% of 20,000 is 600. Mama leaves her original money and the interest in the account for a year. At the end of the second year, the bank will pay interest on the entire amount, 20,600. Since the bank is paying interest on a previous interest amount, this is called compound interest. So we need to create a model for this, right? So why don't we start with a table here. So we've got time, t, right? Number of years. So at the beginning, she started out with how much money? 20,000. Then we added 600 to that, because that was 3%. So after that first year, 20,600. Okay? So, what would be 3% of 20,600? So we'd multiply that by 0.03, right? Because we always turn a percent into a decimal. So let me get my calculator out. And we've got that. So 20,600 times 0.03 would be 618. 618. So we'd add 618 to that. So that would be 2,100 or 21,600, not 618. Okay? Oh my goodness. 218. Okay. Now, if we look at this, this is definitely not arithmetic, right? And we said it was an exponential equation. So shouldn't we be multiplying? So what if we change that to multiplying by 0.03? Is that going to work each time, timesing by 0.03? Well, if we do that, 20,000 times 0.03 we said was 600. Okay, so we're not timesing by that. So how can we think through this? Okay. So, if we're looking at this, think about it this way. Okay, because doing the timesing and adding the number, yes, we could do that, and that would work great. Except when we want to get up to 20 years. Okay, which is not too fun of an idea to do, right? So 0, 1, 2, 3, we need to get up to 20, right? Multiplying each of those new numbers by 0.03% and then figuring out how much to add to that is not the way to do things. Okay? So think about it this way. We're increasing this by 3%. Okay? So we're taking this full amount, which percentage-wise, the full amount is 100%, right? And we're increasing it by 3%. So really, we're taking that amount and increasing it by 103%. So really, we should be times it by 1.03. So if we times by 1.03, if we check that, that gets us our next number. And now we can use that to keep going. So we get 21,21,8, then 21,854 and 54 cents, and we could keep doing that. Or we could make an equation. Remember, with exponential, we know it's the starting number a, the y-intercept, times the growth to the x. So our a would be 20,000 times our b would be 0.01, and we want to get to 20 years, right? So if we put that in using that equation, that's going to get us our result quicker. So putting this in, and we'd get up to 36,122 and 22 cents, which would take way too long just using that table, right? So we can use this equation model, which I think is much better than this. So we'd go y equals 20,000 times 1.03 to the t, because we wanted to do it with time. And maybe instead of y, we should change that to f of t, be super fancy. That's our money, right? Alright, so now let's take a look at the next part. So the next one says we have this formula that we use to calculate the amount of money when it's compounded annually. It's right here. A equals P times 1 plus R to the T. Okay, A is that amount of money in the account, so that would be this amount, would be A. Okay, P is the principal, word for the first number that we start out with. That was this number, okay, 20,000. R is the interest rate. That was the 3%. And T is time of years, which was 20. Okay? So that's kind of how all those pieces tie in together. So it says apply this formula to Mama's bank account and compare the results to the model that you created. Okay, so A equals 20,000 times 1 plus our rate was 3%, so 0.03. Time was 20 years. Okay? So our P was 20,000, our rate was 3%, or 0.03 mathematically, and our time was 20. So we put that in, and we work that out, and we should end up with the same amount, right? 1 plus 0.03 to the 20. And we got the same amount, 36,122 and 22 cents. Okay, so now it says, based upon the work that you did in creating your model, explain the 1 plus r part of the formula. Okay, if we notice, what if we simplify that? Can we put 1 plus 0.03 together? Yeah, because it's inside parentheses, it would be 1.03. Okay, doesn't that look a lot like the one we did? It does. So what does that mean? So that 1 is like the 100%. Okay, because we're taking that amount and adding to it. And we're adding the 3%. That's what that means. That 1 stands for 100%, because when you're finding interest, you don't lose any of that principal. The R, the rate, that was our 3%. You know, add them together, and we're raising it by 103%, or in our case, 1.03. Alright, now let's take a look at this next one. Another common application of exponential functions is depreciation, when the value of something you buy goes down a certain percent each year. It is called depreciation. For example, Mama Big Bucks buys a car for $20,000 and it depreciates at a rate of 3% per year. At the end of the first year, the car loses 3% of its original value, so it is now worth $19,400. Okay, so model the value of Mama's car after T years. So once again, we're trying to figure out how to do this using the same idea. Okay, how long will it take us to be worth less than $500? Okay, so let's apply that same thought process here. So let's make us a table. So we've got a table here, T for years, the value of the car. So we start out, it was worth $20,000. After that first year, it depreciated by 3%. Well, once again, 20,000 times 0.03 was 600. So they subtracted 600 and got 1,000. Oh my goodness, 19,400. Having issues with my numbers today. Okay, so that's going down. So we can't use that same model, that same equation that we did here, right? We've got to do something different. So think of it this way. 20,000 is 100%. Okay, we're decreasing this by 3%. So 100% minus 3% would be 97%, or 0.97. So let's try 20,000 times 0.97. That gets us our number. So see, we're timesing. Instead of it getting bigger, it's getting smaller, so we have to be less than 100% by the 3%. So if we keep going with this model, we get 18818, 18,818, then 18,253.46, and so on. Okay, so there's a model. We could also make an equation again, right? F of t equals our starting number times 0.97 to the t. So now, how long is it going to take us to get lower than 500? So if I keep hitting enter, so I'm going to count here, so that would be 4, 5, 6 years, 7, 8, 9, 10. So at 10 years, we're at 14,748. It's due to 20. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20, we're at 10,875. And I'm just typing these into my calculator and hitting the enter button multiple times. So 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So at 40 years, we are down to 5,914. So this is holding its value very well. So 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. '70 years, we're at 2,371. So let's keep going. Figured you didn't want to keep hearing me talk, just my numbers. I'm at 80, 90, still above 1,000. I'm at 100 years, we're at 951. Okay. I believe 122 years, that was $486.61. Okay, so yeah, it takes a lot of years to do that. 122. Okay, because we're only going down by 3%, that's a really small amount. So how are they similar? Well, they're both growing at 3%. One is growing up, one is growing down, right? The bank was going up, whereas the car was going down, but it was going down by that 3%. Okay, which would be one of the differences we see is the one's going up, one's going down, one's getting more money, one's getting less. One has more money to create more interest with, whereas one has less money. So the more money you get, the quicker it goes up. Because 3% of more money is more. Whereas for the car, the smaller it gets, the slower it goes. Because less money gives you less percent to take away. So it says, consider your model for the value of Mama's car and develop a general formula for depreciation. Well, thinking about this, we took this concept and they just separated it into those two pieces. So thinking about what we did here, we subtracted, so that 1 was like 100%. So couldn't we say the amount it's worth is equal to its principal where it started, and then 1 minus the rate to the t? Would that take into account this? I believe it would, and something like that would be a good way to model that depreciation for any amount of car or anything that depreciates. Alright, so there's kind of the main idea there with using that exponential in a situation where we see exponentials used quite frequently.